some announcements. First of all, the lecture of tomorrow, Wednesday, will start at 12:30 instead of 11:30. Okay, so we have the 26th May lecture starts at 12:30 p.m. Okay, p.m. or a.m. I don't know. 12:30. Okay, just 1 hour later, the standard hours, the standard scheduling. Okay, so I will put a note in the website just to remember you this one, this condition. Okay, so 12:30 up to 30, basically. Okay, and the second announcement is related to the questionnaire about the didactic. So I invite you to fill in the questionnaire about the didactic, which is called the CPD questionnaire, Comitato Paritetico per la Didattica, which is about the discourse. So whatever you think about, say, how discourse is planned and my effectiveness as a teacher, etc., etc. You will know, okay, is something that you now are used to fill at the end of the course. For us, it's very important to, say, collect your indications, okay, to help us in order to build a better next year course. Okay, so feel free to fill this questionnaire, please. Okay. So after these two, if you want, the lecture of tomorrow will be the end of the course. Okay? This is the last lectures. Of the course. So tomorrow we end this course. Okay. So let's continue what we just started a little bit last week. And so the topic is about the brushless DC motor. Brushless DC motors is a kind of motors that is hard to classify as a DC motor or an AC motor. It's something which is in between. As I said in the previous lecture, brushless DC motor has similar electrical characteristic of a DC motor. Okay, but say is a better reliability because the brushless DC motor has no mechanical fixture like brushes, commutators, etc. And it has smaller, let's say, higher efficiency if you want. Higher power density, higher torque to inertia ratio. So for a given level of torque that is similar to that of a DC motor, the inertia is lower, but because simply it has no any additional mechanical heavy fixture, so it is light. So it has, let's say, faster pen is not working, so I have to. Okay. Faster speed response. Higher speed respect to DC motor. And then it has a similar construction to that of an AC motor, which is the permanent magnet synchronous motor. Okay. Similar construction of a permanent magnet synchronous motor, which is called PMSM motor, because it has, say, winding on the stator and it has permanent magnets on the rotor. Okay, winding on the stator makes possible to dissipate heat easily. Okay, because the losses that generate heat, okay, by the current flow into the winding are, say, on the external shell of the motor, so it is, say, easy to, say, make this heat to say radiate into the space. Okay, while in the DC motor, for example, the windings are on the rotor, so they are inside of the motor. It's difficult to extract heat from, say, something which is inside the motor. It's an outer shell which is, say, covering the windings, and so it means that you can get higher power density, for example. Okay, with respect to that. Sometimes, due to this similarity in the construction between a PMSM motors and brushless DC motor, this kind of motor are also called BLAC motors. Okay, that is different from a BLDC motor, which is the brushless DC motor here. So the say similarities that you can have between a permanent magnet synchronous motor and the brushless DC motor ends when you say have a look at the way the two motors are say driven and the way the continuous torque is generated. Okay, because in brushless DC motor, the construction made by using specific permanent magnets, which are specific polarization, etc., make possible to generate a back EMF, which is trapezoidal. This is E, for example, of the phase A. This is something which is proportional to the rotating speed of the motor. Okay, this is trapezoidal. While in the brushless AC motor or permanent magnet synchronous motor, say the back EMF is always sinusoidal at the fundamental frequency. So in order to get a constant torque, having this trapezoidal back EMF, we need constant current flowing through the phase when the back EMF is constant here in this region, as we'll see in the next explanation. While here you have something that should be, say, sinusoidal behavior. This is the current having the same phase. So the similarity in construction do not correspond in similarities in the driving, okay? Because we need different way to drive the two motors, BLDC and BLAC motors, okay? So, for example, in this specific case, we need this kind of current, which is a constant current for a specific time interval in which the back EMF is constant. Okay, the way in which I can generate this current for, say, the BLDC motor is the topic of what I'm explaining, okay, now. So in order to understand how can I generate this current, first of all, look at the current I have here. This is a bidirectional current, okay? So in order to do this kind of current, I need something which make it possible to generate a current which is, let's say, bidirectional, okay? So remember that we know that, for example, the bidirectional converters that we understand, what we learned in previous lectures, will be employed here, okay? Another consideration that we have to make is that the BLDC motor can be constructed by using, say, one phase, so having just two, say, terminals at the output, or can be employed, say, in a three-phase operation, so they have, say, the standard three terminals at the output, or say a higher number of phases. But we have to say that most of the time BLDC motor are operated with three-phase voltage systems, okay? So typically, BLDC motors are three-phase connected. So they are constructed in order to generate at the output three-phase voltages and currents. So they have three terminals at the output. So this leads to the consideration that the electronic blocks that can be employed to be connected to, say, brushless DC motor is the standard three-phase inverter that we already know. Okay, remember that we had these topologies, which is built by three legs in parallel, okay, in this way, a constant voltage here, and then you have three nodes A, B, and C here. Now, the basic difference that's this driving here, which is a standard three-phase inverter, is also the block, the electronic block that I must use for generating this kind of permanent magnet synchronous motor electrical characteristics, okay? For example, the sinusoidal currents, okay? So the block is always the same. The difference between BLDC and PMSM motors is the way I commutate the switches inside these three-phase inverters. While in permanent magnet synchronous motor, all the three legs are simultaneously activated, okay, depending on the, say, the strategy that I want to use. For example, I can use space vector modulation, I can use square wave modulation, I can use sinusoidal pulse width modulation. Okay, the strategies can be different, but all the three legs have a commutation inside, okay, for each time instant. The difference is that in BLDC motor, not all the three legs are activated simultaneously, okay? The basic driving is due in BLDC motors. Only two out of three legs are active at any time instant. It means that two legs, for example, the legs A and B, have, say, commutation, the switch, but the remaining leg is left, let's say, in a specific configuration. Okay, this is a totally different way to use the three-phase inverters in BLDC motors. Okay, while in permanent magnet synchronous motor, all the three legs have a switch that commutates. Here, say, one leg is left in the same, say, specific position. For example, with one of the switches closed and the other one is open, while the other two legs have some switches that commutate. Okay, which of the two legs I have to activate? Okay, because I have to choose time instant by time instant, which of the two legs I have to activate. In order to understand which of the two legs we have to say energize, okay, and which of the three legs I have to say left in the say inalterated, I have to know the position of the magnets in the rotor. Okay, remember that BLDC motors have permanent magnets embedded in the rotor. Okay, I should have some information about the position of this the magnets. So I need information about the orientation of the magnetic field generated by the permanent magnet inside the rotor. And I am going to use this information to choose which of the three legs I have to say activate or not activate. Okay, and in which way I can I can have this kind of information about the position of the permanent magnets in the rotor. Typically, some sensors that are specifically designed in order to say evaluate the magnetic field orientation in the rotor must be used. Okay, so let me just put here the legs to be activated are chosen on the basis of permanent magnet position, and these require sensors to evaluate magnetic field orientation. Okay, so what kind of sensor I can use? Typically, I have to use magnetic sensors that are called all effect sensor. Let me just to share the slide, because in the slide I have a better drawing. Now you should see the slide. Okay, here you have in the bottom of this slide, okay, a very simple and simplified view of an old sensor, which is typical an element which is made by a semiconductor device that is powered, so it has a supply voltage, and so we have a current flowing through it. The current is called IH, and this material is subjected to a magnetic field represented in this figure by the arrow of this B field. Okay, this is the magnetic field density. Okay, crosses the surface. Then we have two other terminals, another pairs of terminals here. Okay, across which we can measure a voltage, and this voltage depends on the intensity of the magnetic field that crosses the surface of this all element. Okay, VH is something that we can measure. Okay, VH is proportional to the intensity of the magnetic field B by means of several parameters. For example, RH, which is a constant, okay, the all effect constant, D, which is the thickness of this material, IH, which is the current flowing through it. Okay, so supposing that my material is, say, as a specific time constant RH, it is made by a thickness D, and the current is IH, though this VH is directly proportional to B, okay, this intensity. So for example, I can use this all sensor to understand if the B magnetic field enters from the top and goes to the, say, bottom of this material, or it is reverse directed from the bottom to the top. Okay, in that case, the voltage VH reverses its polarity. Okay, so simply looking at the polarity of this voltage, I know if the direction of the magnetic field points, let's say, downward or upwards, for example. Okay, suppose that for my explanation, I have a Hall effect sensor that outputs a digital signal. Okay, and this digital signal can be, say, 1 or 0, high logic level or low logic level. Okay, and then suppose that my logic level is generated anytime I sense the north pole of my magnetic field generated by the permanent magnet. And this sensor outputs a 0, logic level, when you detect the south pole of this magnetic field. Okay, so for two different orientation of the field, I have 0 or 1. So this is the way in which I can understand basically the direction of the magnetic field generated on the rotor by the permanent magnets that are embedded in the rotor, say, construction. This information must be combined with, I have to use this information basically to understand which of the two phases of my three-phase inverter I have to activate. Let me put this say, this concept in a very easy way. Okay, in this system here, I have simply a three-phase system that I can call U, V, or W, or ABC, for example. Okay, ABC can be, say, the 3 nodes that you can have at the output of these inverters. Okay, and then I schematize these three-phase in this way. We have just this kind of inductances, okay, put in this way. Okay, the green arrow that you can see in this cross section just symbolize the current flowing through these phases. Okay, so for example, in the figure that you can see here, there is a current that enters U, okay, and exits W. The current goes in this way. There is no current in the phase which is called here V. This means that the V phase is not activated. The V phase is left open. Okay, for example, suppose that V is the C. Okay, then you have two switches here that are open. T5 and T2 are, let's say, open. There is no current exiting here, but you have, for example, the current flowing to A and B. So this is the meaning of having just two legs in which, say, there are some switches that are activated, so they are closed, while the left, the remaining legs is left, say, basically is left open. Okay, so here you have two of these legs that are activated, making a current flowing to the phases, and one, the V phase, is left open. Okay, so this happens time instant by time instant. What is the, say, effect in doing this kind of driving? Is the effect is that the current flowing just to 2 out of 3 the phases of the BLC motor. So in that situation, the phases are arranged, say, mechanically constructed in such a way to generate a specific magnetic field in the stator. Okay, the stator magnetic field has a specific direction which depends on which of the 3 phases are excited. Okay, for example, in this specific situation, which you have U and W phases on, and V, which is left open, the current flow is in that direction, and the resulting stator magnetic field has these, let's say, orange, pink, I don't know which is the color here, directed arrow. Okay, this is the North Pole. Okay, so this is the South Pole here, and this is the, say, mode number 1 that I have here. Okay, in which the flux which results from the flowing of this current is directed in this way. Of course, if I exercise other 2 phases, okay, the field, the magnetic field, the stator magnetic field generated changes its direction. Let me just to share. Let me see if it works. Can you see something? Can you see something rotating, especially? Can you see something that works? This is a GIF. Okay, that's good. Thank you. As you can see here now, I put in this, say, GIF, an animation which you have just 2 phases out of 3 that are excited. The third phase is left open, so no currents flow to that winding. And so, as you can see, for each combination, then you can see a different orientation of the stator magnetic field generated by the current flowing through the 2 phases, the 2 windings. Okay, as you can see, the same U and W phase that are, say, the phase, the energizing mode number 1, okay, can be activated in 2 different ways. When the current goes from U, entering U and exiting W, you can have say, this resulting flux here, the number 1. But the same 2 phases can generate a different orientation of the field, okay, when you have the current that enters W and exiting U. So by made the current to be reversed, the direction of the current is reversed, the direction of the resulting flux is different. Okay, for example, look at the phase number 1 and the mode number 4. Both of these 1 and 4 modes involves the phase U and W, but the resulting flux are, say, opposite direction. So basically, I have, say, 3 possibility to excite 2 phases out of 3, but then I can reverse the current, or I can get 6 possible different combinations. Okay, and 6 different possible combinations make possible to generate 6 different orientation of the stator magnetic field. Okay, and these possible orientation are indicated here. As you can see now, I able to generate a rotating stator magnetic field, okay, by activating these 2 phases out of 3. And this position, okay, are, say, distance basically 60 degree one of the others. Okay, so I have set 6 steps, and 6 steps make possible to originate a sort of, say, rotating magnetic field, but the rotation is in discrete way. Okay, I have just 6 vectors that are separated 6 degree one from the others. Okay, so this is the way to generate a rotating magnetic field. Now I have to combine this information to what I said before. In order to understand which of the 2 phases I have to energize and which phase I have to left open, I should know the information about the position of the rotor. Okay, and the position of the rotor means that I just have to sense the position, the orientation of the permanent magnetic field generated by the magnet inside the rotor. And this can be done by using specific sensors that are the Hall effect sensors. So I have to combine these two information. Okay? This one is the position of the rotor, and then on the basis of the position of the rotor, so the signal, digital signal at the output of the the Hall effect sensor, I have to choose which phase I have to energize. And this is the mechanism by which I can get a constant torque. Let's have a look at what is my specific example I want to use for describing, say, the combination of the Hall effect sensor information and the driving techniques that I have to use. In this slide, you can see that I have these 3-phase systems, okay? And then you have these, BLDC motors, okay, the cross-section. The example here is made by a 3-phase brushless DC motor. So we have the phase A, the phase B, and the phase C that are similar to the phase U, W, and V in the previous animation. And then I have 2 poles. So 2 poles means that I have just north and south poles in the rotor, okay? So you have 2 poles, 3-phase brushless DC motor. Of course, 3-phase is a system that you can, say, find easily in several applications. Maybe the number of poles typically are larger than 2. Okay, you can have 4 or 6 poles, etc. But this is just for not complicating too much the understanding. Where are placed the Hall effect sensor and how many sensor I need? For this kind of motor, I need 3 Hall effect sensor that are called H1, H2, and H3 that are there in the stator. Okay, so they are fixed in space. They are, say, accommodated in, say, in the stator, which is, say, not moving. And then you have 2 poles. Okay, they are shifted H1, H2, H3 by 120 degrees. So they are equally spaced in the stator. And then you have north and south poles. Okay, so let's have a look of these other document that I want to share. Can you see here the a cross section of these 2 poles 3-phase rotor motor? Here you should see a PDF file with this. Okay, suppose that I am in this situation. Okay, I have this is the cross section, so the blue and red semicircles here are representing the permanent magnet, the south pole and north pole embedded into the rotor. Okay, then I have on the outer circular surface H1, H2, and H3 that represent the Hall effect sensors, and then I have A, B, and C that represent the 3-phase, the winding of the stator. Okay, so of course this is a simplified version of a schematized version of my brushless DC motor. Okay, I have this specific situation. Suppose that I am considering the output of my Hall effect sensor as digital 1, high logic level, when the sensor detects the north pole of the permanent magnetic field. Okay, so for example, in this specific situation, I put a green, say, color inside the squares representing the Hall effect sensor because they are outputting digital 1. Because, as you can see, the 2 Hall effect sensor H1 and H3 are under the influence of the, let's say, north pole of the permanent magnet, the red one. Okay, so H1 detects this north, H3 detects this north, so these are one logic level. H2 is under the influence of the south directed permanent magnet field, so it has a 0. So H1 1, H3 outputs 1, H2 outputs 0. Okay, now suppose that I'm exciting the phase that are B and A, and the phase C is not activated, it's open, no current flow here. So the current can flow just through the phase A and B, a current entering the node A and exiting the node B. The current is the same, okay? So the current I is the same current flow into the entering A and exiting B. If you consider this specific, say, excitation mode and excitation mode, then we are able to generate a specific direction of the stator magnetic field, which is indicated by this arrow, the red arrow. So the red arrow here represents the point of this arrow, represents the south of the magnetic field generated by this. Okay, so this arrow here is the specific arrow direction that has 6 positions separated by 60 degrees. Okay, remember the GIF I presented to you before. So, okay, in that specific combination, the vectorial combination of the currents flowing through phase A and B generate this specific direction here. So the red arrow represents the position, the discrete position of the stator magnetic field. The rotor is rotating, and that specific photo, the specific frame I just illustrated to you, the Hall effect sensor are H1, H3 have an output digital, which is 1. Okay? So let's have Okay, this is the position I indicated here. So you have in the operating mode number 1, I'm activating A and B. I'm indicating here A plus because the current is entering A. Okay, and for my convention is to have a plus when the current enters the nodes. The node. Okay, so A plus means that a current, positive current enters the node A. B minus because the same current exiting the node B. Okay, so you have A plus, B minus. The VH1, VH2, and VH3 that are, say, here represent the digital output of the sensors. Okay, so VH1, the output of the sensor H1 is 1. The same happens for VH3, which is 1. VH2 is 0 because it's under the influence of a south pole. So my hypothesis is that I have 1 when I detect north and 0 when the Hall effect sensor detects a south pole. So let me just give these following 3 plots that represent the back EMF and the current flowing through the phases. Okay, so I have the current IA, the red one, which is equal to I. The current IB, which is negative I, okay, because the current is exiting. IC, which is the current in the not activated phase, it's left open, is 0. Okay, so in this configuration, IA, IB, and IC are all current that enters. So IB is a current that enters node B, IA is a current that enters node A, and IC is a current that enters node C. For this reason, IB is negative, okay? Because since IB is a current that enters node B, but now the current I is exiting, IB is negative I, okay? In that specific situation, the back EMF, the motor is constructed in order to have a constant back EMF due to the phase A, a constant negative back EMF due to the phase B, while the phase C as not a constant back EMF is something that transitates from one value to another value, to the next constant value. Okay, but just focusing on these two, AI and AIB, EA, and EB. Because if you want to talk about, the torque, okay, the torque generated by the phase A, as I say, described in the lecture the last week, is the product of the electrical power, which is the product of AA and IA, and this is constant because I have IA, which is the red one, constant to level I, and the back EMF, which is constant by construction, divided by the rotating speed. TB is the same. Now the product is between two negative value here. Okay, and so you have positive torque TB. The torque TC is null because the current IC is null. But if you want to get the total torque, you have to sum up TI, TB, and TC, and you get something which is, say, positive. Okay, is the product of the total electrical power at the phase divided by the constant velocity omega m. This happens for the phase. Then move to the next situation. As you can see here, between this position, this one, there is a little rotation anti-clockwise of the rotor. Look at the north and south colors in the rotor. Now I have, say, a little bit, a shift anti-clockwise. Something changed in this description? No, because say H1 always output a 1, H3 is always under the influence of the north pole, so output a 1, H2 is, say, 0. So the information about the rotor position are the same as before. So nothing changes in my, say, current and voltage description. Let's move a little bit clockwise directed. As you can see now, I have a little, say, movement anti-clockwise direction, but basically there is no difference, okay? Because H1 and H3 are always under the north directed say, stator rotor magnetic field, so the same output, digital output at the sensor are, say, generated. So nothing changes, so the current is always the same, the back EMF is always the same, etc. The torque is constant to that value. Now move to another position, okay, which is 1, this one. Now this one is the last position which you have H1 and H3 that are on, okay, because as you can see, H3 is exactly in between the north and south pole, okay. So here you have, say, nothing different with respect to before. So the phases A and B are the same phases I activated before. So we are still in the operating mode number 1. But now something changes, because if you made another step of rotation, okay, now we can see that now the H3 sensor is under the south influence. So it detects there is the south polarity of the generated magnetic field by the permanent magnet in the rotor. So it outputs 0. So as you can see, now there is a transition here in the VH3 here, okay? The transition from 1 to 0. What about the all effect sensor H1? It is always under the north detection, so VH1 is still 1. VH2 is still south. Okay, so the only difference now is that VH3 is going to 0. Okay, there are just one all sensor that outputs the 1, which is H1. The other two output 0. But this changing here is, is the information that I need to understand that something changed. And this information is employed, okay, is fed back to a controller that change the phases that I have to activate. Okay? Before this situation, I have the phase A and B activated, and the phase C was, say, open. Now, thanks to the variation of the H3 sensors, okay, I use this information to move from the operating mode number 1 to the operating mode number 2, in which I activate A plus and C minus. So I change the two phases. Okay, basically the phase A is still activated, but now I move from B to C. A plus, the current enters A and exiting C, C minus. This is then phase number 2. What happens when I change the two phases that I'm energizing? That the stator magnetic field changes its direction 6 degrees counterclockwise, okay, from the previous position, which is this one. We see here, the S here, okay, here. Now I have this one. Okay, I change a little bit 6 degree anti-clockwise direction, okay? So as you can see now, the phase B is not activated, so the current flowing through B is null, but now I have a current negative I flowing to the phase C. So the torque, which is the total torque developed by the motor, now is due to the torque developed by the phase A, TA, and the torque developed by the phase C, TC, while no contribution is given by the phase B, TB is null. But the summation is always the same. So the torque, the total torque, the overall torque TE developed by the motor is constant due to the fact that I'm summing the torque of two phases out of 3. Okay? Now it's happened that when the current flowing to the phase C is constant, even it is negative, I see the green curve here is constant, the back EMF is the back EMF of the phase C, EC, is made to be constant. While the phase B, which is not activated, has a, say, transient, okay, which is the transient that makes possible to move from the previous static value of the back EMF to a positive value, which is held in the next phase. Okay, but is not important because the current flowing to the phase B is null. So this transition of the back EMF, EB, does not produce any torque because the current is null. Okay, so only the torque which is generated by the current, the constant current. But anyway, move again. You have the same situation as before. I move a little bit the rotor. Okay, as you can see, H1 is always 1, so nothing changed with respect to before. Now I move, say, abruptly from another situation that you can have here. But this situation is a situation that brings H2 to become 1. H2 becomes 1 because now it's under the influence of the north-directed rotor magnetic field. So now we have H1 and H2, which outputs a 1 signal. This is, so you can see here, VH2 has a transition here, okay, that goes from 0 to the 1 digital level. The other two signals, H1 and H3, are always, say, the same as before, 1 and 0. But this rising edge is, say, depicted, is sensed by the controller of my inverters, and this is the, let's say, the signal that we're waiting to change the operating mode. From the operating mode number 2, I change to operating mode number 3, in which I change the two phases that I have to energize. Okay, so from A plus C minus, the phase, the operating mode number 2, I move to B plus C minus, which is the operating mode number 3. And these have as a consequence that my, say, magnetic field generated by the stator has another 6-degree anti-clockwise rotation, and is here, okay? As you can see here now, the B phase has a constant current, positive current, it enters, and so it has a back EMF which is constant. Now is the phase A, which is left open, so no current flowing through it. The back EMF EA has a transient, a transition between the positive level to the next stable value. What about the torque? The torque now is due to the contribution of TB and TC. The summation is always constant. Okay, so the torque, the total torque is always constant. And then you can go further to other situation, for example, this one, which you have, say, H2, which is, say, 1, while all other two sensor output at 0. So basically, you have these, let's say, information here. The fact that the VH1 now goes to 0. This information is employed to change the phase. Now I have B plus A minus. And as a consequence, I have another 60-degree step anti-clockwise of the stator magnetic field, etc., 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 etc. Okay, and then we pass through all the 6 operating modes. Basically, let's say, the situation is, say, can be summarized in this way. I generate a, say, rotating magnetic field, okay, in the stator, and the position of the rotor sensor basically, say, are following the position of the stator field. Okay, so the rotor is moving continuously by, say, in the attempt to follow, to run, say, along the variation of the stator magnetic field. Okay, it's something like having, let's say, a donkey with a carrot, okay, near the mouth, and it's try to, say, follow the carrots in order to make the donkey moving. Okay, something like this. Okay, I move the rotating field in order to make the rotor, the stator field, in order to make the rotor moving. Okay, changing continuously the phase that are activating. Is this process clear? There is something which is not clear. I just, say, considering this description totally, say, intuitive and graphically explained. Okay. Have you some questions about this explanation? Something which is not clear? Is everything okay? Okay, good. Okay, let me just move to the, okay, it's here. This one. This explanation is also indicated here. If you want, I can put the say animation and the slide I show you in the materiale section, okay? Just to have another support for this explanation. Okay, here is indicated my explanation. So just two things to be discussed here. One is how about the model of my brushless DC motor? Okay, how can model this input, say, electrical gate of the motor? Basically, there is the same model of say any kind of other models. Okay, let me just say discuss this a little bit, very fast explanation that whiteboard. Okay, what about the model of the motor? Simply, you can model one phase of a BLDC motors, just having the inductance of the phase, supposing this is the phase A, okay, the resistance of the phase modeling the losses, and the back EMF. EA, for example, and this is the current IA. So this EA is proportional to the rotational speed. So basically, this is the model that we already use for DC motors or AC motors, and nothing changes. And again, I can use the voltage VA as a means to vary the, say, the speed, for example. Okay, so if you have the possibility to change this electrical characteristic here, modulating them in order to vary, for example, the amplitude of the back EMF, and so you change the omega speed, the rotational speed, etc. So you can act on the mechanical characteristic of the motor, say acting on the electrical characteristic you have here, exactly how we did for any other kind of motor. Okay, this is the basic, say, way to say modulate and to adapt your supply of the motor to the characteristic of the BLDC motors. Okay, there is a say drawback in this operation of the brushless DC motor. The drawback is that BLDC motors can have a significant torque ripple during the phase commutation. Okay, remember that we have 6 operating modes. Okay, 1 from 6. When you change from 1 to 2, or from 2 to 3, etc., so we are changing the operating mode, then you can have a significant ripple in the torque. Okay, in my previous explanation, the torque TE is always constant. Okay, but this is not, let's say, something that we can obtain practically. Okay, let me just discuss a little bit this topic. Okay, the torque torque TE is given by what? The electrical power divided by the rotational speed. Okay, so that means that I have the TE. This comes from this expression. This is the mechanical power. The product of the torque and the rotational speed gives you the mechanical power. So in an ideal situation, which we are, say, considering that all the electrical power I'm providing to the motor is transformed to mechanical power, PM is equal to P. Okay, so I can have this expression. P is the summation of the 3 different contributions of the electrical power provided by the phases. Okay, so we have 3 phases. So we have EA multiplied IA. So this is the electrical power for the phase A. Then EB multiplied IB plus EC multiplied IC. And then this is divided by omega. Okay, this is the exact expression that I show you in the previous explanation of the torque generation. Okay, just remember two things about notations. Okay, this is the phase A, B, and C for these 3 phases. I considering the current IA here sorry, C. Maybe this is B. And this is okay. IB and IC. Okay, my notation is that I consider in positive the current that enters. Okay, so these three currents indicated here are the positive current. What about, for example, I don't know, the operating mode number 1? In the operating mode 1, what I have? I have A and B excited. Okay, so I have that the current is this one, and the current is I. So in operating mode, I have IA, which is I, the direction is concordant to I, IB, which is negative I, and IC, which is null. What about the voltage? The voltage EA is, let me put this constant to value E, okay, is a constant back EMF. We have a constant current, so we have a constant back EMF. So we have EB, which is constant to a negative value, which is, say, the opposite of that you can have in the phase A. So you have negative E. And in the phase C, you have something that is not, say, is something that changes. Okay, something changes in this way from negative E to E. Okay, but it's not important because the current here is null. So in operating mode number 1, so TE, in mode equal to 1, then you have E that multiply I plus another E that multiply I divided omega n. So it's 2EI omega n. Okay, it's a constant value that depends on the back EMF, on the current flowing to the phase, etc. So let me just consider what happens when you are changing, you are in the transition between two different operating modes. Okay, what happens during mode change? So let me just consider whether, for example, from mode number 2 to mode number 3. Okay. Okay, let me just look at what happens to remember what are the phases that are involved. Okay, we are in the phase number 2 here, and the number 3, which is here. So in the phase number 2, I have that I'm starting with a current which is IA, as you can see here, is equal to I, IC, which is equal to negative I, to a situation which I have IC, which is again negative I, and IA, which becomes null, and IB, which is negative I. So let me just consider this transition. So I have that the torque TE, which is, say, AI multiplied AI, the same formula as before. I have that EA, the back EMF of the phase A is equal to, I'm just looking at the transition, okay? The transition between the phase 2 and the phase 3 as the current A that, say, has this behavior. Let me put here, IA is from, in the phase 2 is equal to I, and the current B is 0. Then I have the transition, okay? And I have to put here the phase 3. And at the phase 3, the current A would become 0. And the current B from 0, it becomes I. Okay, so this is the level of the current. So you have 0 here and I here. So you have this specific transition for the current IB and IA. The current IC is always the same. The current IC is, say, the current IC. IC is equal to negative I, but is not changing. Okay, so during the transition between the 2 and 3, there is a changing in the current between the phase A and B. Okay, this transition, my previous explanation was, say, instantaneous. Okay, so I changed this quantity instantaneously. Let's have a look what I showed you before in this phase. There is a graph showing you the no graph here. But anyway, look at this phase here, the phase 2 and 3. Okay, as you can see, look at the current between 2 and 3. As you can see here, the current IA goes from I to 0, as I said before. The blue current goes from 0 to I. So the two currents, say, change their values. The current IC is always the same, as I said before. And this transition I put here is totally instantaneous. Okay, the current goes immediately to 0 or to I in the, say, no time interval. Okay, this is not possible because we are in a system which we have inductances. And so remember that the inductances try to do whatever to maintain the same current flow. So this, say, I steep transition, the I on the T very fast, is not possible. Okay, so you have something that changes, but not with that rate. Okay, so we can say that here the current from this value goes to another value, but this changing happens in a specific time interval, delta t, which is not 0. Okay, so this is the problem. Okay, what happens in this interval? Okay, but basically you can have several different situations. For example, you can have that I don't know, the phase B can be faster than the phase A. Okay, for example, you can have a situation in which the phase B goes to the final value in a transition time which is less than that of the phase A, because, I don't know, depends on the way you are driving the phase. Maybe the inductances are not exactly the same. So it can happen in a practical system. So this happens, this can happen. So whatever, what does it mean? It means that basically you have a situation in which the summation of the two currents is not constant. If you look what happens in the ideal situation, the current IA plus the current IB, so the summation of these two currents here, IB and IA here, provides always negative IC. Okay, IB plus IA is always negative IC. But if you have these, say, different rising behavior for the current IB, then this summation is not, say, negative IC. So what does it mean? That you have this expression, this formula, EA and EB during this transition is equal to E. And then you have IB plus IB here, because EA and EB is equal to E during this transition. Plus you have something which is negative E multiplied IC. Okay. If IB plus IC is negative IC, then you can get something which is 2E over omega m multiplied IC. Okay, and so IC is constant to negative I, so the torque is constant. But anytime this summation here is not equal to negative IC, then this torque depends, say, on say something which is not constant. Okay, because the summation is not more equal to IC. So that means that in that situation, the overall torque is not constant. The overall torque can be something like, I don't know, something like this. The overall torque T, which must be constant, is something that, for example, rise up a little bit. Is a little bit higher. There is a ripple in the torque. Okay? The torque that I previously showed to be always constant has a specific ripple anytime you change the operating mode. So it happens 6 times for a complete revolution. Okay, so any, let's say, 6 degree, you can have this torque, and this depends on the way you can have these different rising up or down for the current. Okay, for the current flow into the phase that are changing. Of course, this can be something that can have some, say, influence on the behavior. And so you can several different solutions have been elaborated in order to avoid this problem, because this problem can induce, let's say, even acoustic noise. Can, for example, I said before that the brushless DC motor can be very fast. Okay, but typically when you have this kind of torque ripple, then you cannot have a complete range of variation of the speed from very low speed to large speed. So the speed operating mode is something which is limited by the presence of this ripple. And so this is something that you have to eliminate. And so there are several techniques that eliminate this kind of behavior. They are called ripple compensation, techniques. Basically, how can you compensate this ripple? You have to equalize the rate of change of the two currents, because the problem is due to the fact that you have two different slopes for the rising current and the descending current. You can have this situation here, or then you can have something which is lower, okay? You cannot get the same problem. You have to equalize the two rates, and this can be done simply by changing or modulating the voltage that you are applying to the motor. Okay, so the voltage that you can apply to the motor, so the voltage that you can have at the output of your inverter must be somewhat modified in order to compensate for this rate. Okay, for example, when this rate here is dI on dt. Okay, so what does it mean? That you know, you have this value in dt as an impact on the voltage across the inductance of your phase. Okay, you have V dI on dt. This voltage here, which is the voltage across the phases, so the voltage across the winding of the phases here, okay, is something that you can modulate, and it depends on the voltage, for example, that you can have between these two phases. So if you can change the voltage that you can have, for example, between the phase VAB, let me say, a little bit, then you can modulate this voltage across the inductance. So you can change this voltage here. And if you change this voltage here, L is constant, you can modulate this di on dt. Okay, so is say basically a complicated compensation matter in which you change the voltage at the output of the three-phase inverter in order to equalize the di and the t for the different phases. Okay, but in that situation, you can be able to compensate the ripple to avoid this kind of behavior that I said before happens every 6 degrees, so 6 times for a complete revolution. Okay, this is the classical drawback of the BLDC that can be avoided by these compensation techniques. Have you some questions about this this discussion here? Something which is not clear? Of course, my explanation here is very, say, qualitative, say, description. There is not my intention to give you, say, construction details or, say, very, let's say, specific way, but just an overview of what happens in this kind of motor, just to complete, say, the ranges of motors that I described in this course. For people who want to, say, have more details, I can give you some, say, references, in order to, say, expand or to give more insight into the behavior, the operating principle of these motors. Problems, questions? Okay, guys, I will stop here. Okay, basically we have say half an hour to spend, so I don't want to, say, break my explanation. It's better to, say, start tomorrow. Tomorrow we have just 2 hours. I don't know if I'm able to, say, cover all the 2 hours from 12:30 to 2:30, but for sure I will finish Brushless this motor. Then I will have a little talk about the examinations, okay, in order to make clear. And so I am open to, say, questions. And if you want, I will also open for, say, a question and answer lecture that we can, say, arrange in the next week. Okay, we have just basically we have 9 hours left, say, in the, say, scheduled. So if you want, you can have we can arrange a question and answer cumulative for all of you that have some doubts, maybe in the last week, maybe of the course. Okay, just to have the time for you to collect all the questions, doubts, whatever. Okay, we can talk about these topics tomorrow. Remember, 12:30, not 11:30. Okay. Thank you for your attention. Bye.